When we have numerical data, there's another type of graph that we can make called a box plot, or sometimes it's called a modified box plot, or sometimes it's called a box and whisker plot. There's a few different names for it. What we're going to do here is look at if we have these exam scores for a Math 243 class at PCC, how can we build this box plot? So first thing we need to do is collect some statistics. We need to start with our 5-number summary, and then once we have that, we can calculate the interquartile range. So just to go through how we find these values, so for our 5-number summary, we start with our minimum, which is 31, and then we're going to need our first quartile, median, and third quartile, which in the technology video, I'll go through how to find those using technology, but for right now, let's go through how to do it by hand again. So for the median, which is what we have to start with, we need to find the middle. So it's just a matter of taking off values from either end until we can see where our middle is, which is exactly at 82. So that right there is our median. To get Q1, this is where we treat that value of 82 as kind of this barrier between our lower 50%, upper 50%. So using just the lower 50%, we go through and find that middle piece, which is going to land exactly at 70, is going to be Q1. And then for Q3, using the upper 50%, finding that middle value, which is going to be exactly 94, and that'll be Q3. So for our 5-number summary, we'll have 31 for our minimum, 70, 82, 94, and then our maximum is 100. So for our interquartile range, you take Q3 minus Q1, so we're taking 94 minus 70, which is 24 for the interquartile range. So those values get us started with our box plot. In fact, what we can do is even start drawing the box plot. So first thing we need to do is start with a number line for our data. So we're going to draw a number line. We need to start C as low as 30 and C up to 100. So we're just going to make a number line. I'm using a scale of 10s here along the axis, since that should cover pretty nicely. You have to use a consistent scale. Again, you can't just plot the numbers that are from the 5-number summary because we need to see the spread of the data. So that'll tell us some behaviors that are occurring. So along that number line, we're plotting our exam scores. Now the box plot kind of floats above this number line, but we use this number line as a way to figure out where these values landing. So what we do is we draw a box using the median, Q1, and Q3. We draw these tall lines at those locations. So Q1 is at 70, so I'm going to draw this tall line above our number line to represent what's happening at 70. I'm going to draw a tall line at 82 for our median, and a tall line at 94. And then what we do is we connect them along the bottom of those lines and along the top. So we end up with this box that looks like it has 2 sections to it. But it starts at Q1, that middle line is signifying where the median's landing, and then it ends at Q3. So it's a way of showing where that middle 50% of the data is occurring. And in fact, we can see our interquartile range right here. It's going to be the length of this box that is drawn. Now, before we can get to the whiskers part of it, so this is the box part, and then we want to draw the whiskers, we need to see if we have outliers or not. And to test if we have outliers, we need to use the interquartile range along with our quartiles. So for the upper fence, what we do is we take Q3 and add on 1.5 times our interquartile range. So for our scenario, we're taking 94 plus 1.5 times 24. And remember your order of operations here. You have to multiply that 24 by 1.5 first, and then add it to 94. So when we plug that into a calculator, we're going to get 130. And then for our lower fence, we take Q1, which for us is 70, and subtract 1.5 times our interquartile range, which is 24. And that's going to be 34. So this creates a lower fence and upper fence for our data. It's basically giving us a range of values that we expect for our data. But if anything lands outside, that's going to be considered an outlier. So let's take these numbers up to our actual data set. So 34 as kind of a minimum value, that's landing in between our data values 31 and 62. So I'm just going to kind of draw this line here that 34 is landing between those, which shows that 31 is outside of the fences. And that maximum of 130 is actually past our maximum value of 100. So with 130 being past 100, we're not going to see anything extreme on that right-hand side. We're all good there. What we can see is the special value of 31 is causing some issues. So with the fences, that tells us that 31 is an outlier. The fences are just imaginary lines that tell us what's an outlier and what isn't. These numbers, you never want to draw these on the box plot. They're not actually part of our data. Our box plot's just going to be displaying data from our actual set. So these numbers are just to help us out as kind of guidelines, but that's it. The formula that's coming through here, so the formula, this is what we always use, that 1.5 is always 1.5. And what it's saying is that interquartile range is the length of this box here. It's that middle 50% of our data and how far it ranges. So what that's saying is that, okay, if this is kind of the spread of our data with that interquartile range, if we start at Q3, we're comfortable going 1.5 times that distance above. And with Q1, it's kind of like starting at Q1, take that distance. If we go 1.5 times that distance, that's far enough for our data. But if anything goes beyond that, it's too extreme. So where we saw 31 is outside of that distance, that's where we need to draw an outlier. And you can do this with just a dot. I use a little star to signify this kind of special point. With the outliers, you want to draw it as a separate point from the data, disconnected, to show there's something extreme happening there. From there, we draw the whiskers. So we want to use the minimum and maximum. However, you want to exclude the outliers when drawing the whiskers. So our maximum value is 100. It wasn't an outlier. So for this upper whisker, we would draw a line up to 100 and then stop it right there at that maximum value. For our lower whisker, it gets a little tricky because we had this outlier. So if we go back to our data set, what you want to do is, where 31 is an outlier, what if we removed that from our data set? What's our new minimum value? And that would be the 62. Again, we do not use that 34. It's not an actual data value, so we have to use that 62. So our minimum would be at 62, and we just connect that to our box for the two whiskers. And just be sure to not connect the outlier. It has to be all alone out there. And that's how we draw a box plot. So once we have this, we can start describing our data and describing it with 4 features, describing the shape, center, spread, and any unusual features that we found. So shape, that's where we try to describe, is it symmetric, left skewed, or right skewed? So looking at our box plot, what we can see is our outlier, and we have this kind of tail on this left-hand side. That's showing that we have a left skewed graph. It would be symmetric if we didn't have that outlier. If you have fairly even whiskers without any outliers, then that would be symmetric. And it would look like right skewed if we had some outliers on the right-hand side, or kind of this long whisker on the right-hand side. But for us, we have left skewed. So the exam scores are left skewed. And as soon as we determine the shape, that helps us determine how we're going to describe center and spread. If I had said the exam scores are symmetric, then I want to use mean and standard deviation for my description. But because it's skewed, that's where we want to use median and interquartile range. So the exam scores are left skewed with a median score of 82. With an interquartile range of 24. And then for unusual features, just make note of anything strange going on, which for us is typically going to be outliers. So we want to bring up that we have an outlier here. There is an outlier score of 31. And that would be a complete description of our distribution, describing that shape, center, spread, and if there are any outliers or not. Something we can do is graph side-by-side box plots, and sometimes they're shown in this vertical format. They do the same thing, just pay attention to that number line that's occurring. But we can graph them side by side, so then we can do a comparison of medians and quartiles and minimums and maximums. We can get all sorts of information and see how they're landing compared to each other. So with these side-by-side box plots, first thing we're going to talk about is which class had the lowest cumulative college GPA. So with that, we're looking at the minimum, which is on the lower end of this number line. So comparing the box plots, looks like sophomores may be up close to 2, juniors is down towards like 1.6-ish, and then seniors looks like that's also up at 2. So in terms of the minimums, juniors, it's dipping lowest compared to the others, so they're going to have the lowest GPA. And then approximating that GPA, let's say about 1.6, just as an estimation of where we're landing on that number line. Which class had the highest median, and what is that GPA? So for the median, we're looking at this middle line for each of the boxes, and we want to see which one is highest. So which one's highest on the number line, and that's happening with sophomores. It looks like they're up at about 3.2 or 3.3, and then the others are a little below 3. So that's going to be sophomores at about 3.2, just as an approximate of where we're landing on that number line there. And which class has the largest range for GPA, and what is it? So for largest range, we're looking at the length of the box plot, from minimum to maximum, which has the largest distance that it's covering. And with these, sophomores is pretty long, but we can see juniors is longer, and then seniors is actually the shortest. So seniors would have the shortest range, sophomores in the middle, and then juniors have the largest range. And then to estimate what it actually is, we need to estimate the maximum value, which looks like it's probably landing at 4.0. And then subtracting away that minimum, which we'll say is that 1.6. So it should be about 2.4 for that range there. Then what is the most symmetric set and most skewed set? So for these, we want to look at the whiskers and kind of the proportion between the whiskers. If it's symmetric, the whisker should be about the same size. Same size and no outliers would represent a symmetric set. Most skewed would be a large difference between the whiskers. So for the most symmetric set, that looks like it's going to be seniors. If I look at that lower whisker and upper whisker, they look like they're about the same size. So seniors are going to be most symmetric. And then for most skewed, sophomores have a very short upper whisker and a very long lower whisker. So there's a big difference between those lengths. Juniors has a small difference. That upper whisker is a little smaller than the lower one. However, it's not a big difference. So with that, it's not very skewed. That might be even close to somewhat symmetric. But sophomores is showing a very skewed distribution because of such a big difference between the lengths of those two whiskers. So for the most skewed, that's going to be sophomores. So that's how we draw box plots, and then how we can compare them by graphing them together on a single graph.